AP Chemistry students. Hope everybody is enjoying their somewhat of a snow day and staying warm and safe. So before we get started on our notes, I just want to remind you, make sure you upload your homework from the other day, the heterogeneous equilibrium worksheet, to this today's Schoology page as a PDF. And then after taking the notes, the homework for today will be the corresponding worksheet on 15.5 equilibrium concentrations, and that will be due on Monday. And you can either print it off and turn it in on paper, or you can do it on Notability and upload it to this to the Schoology page for Monday. And if you haven't noticed already, I did switch around Monday and Tuesday's itinerary. So on Monday, we're going to do the equilibrium lab. And then on Tuesday, we'll have a quiz over Chapter 15 and then get started on the second part of this unit with Chapter 17 and KSPs. Since we weren't meeting today in person to be able to go over this, I wanted to give us an extra day before having the quiz, and we'll have time before or after the lab to go over this stuff in more detail, because I'm sure you'll have questions. So we're finally going to put some numbers and do some calculations with those equilibrium expressions we've been writing from the beginning of this chapter. So you will need calculators for this. And we're finally going to do some number crunching. So when we don't know all the equilibrium concentrations, because again, we're to calculate an equilibrium constant, we need to know concentrations or pressures of all of the substances at equilibrium. But oftentimes we don't know all of those. But as long as we know at least one of the concentrations and either the Kc or Kp, we can use the stoichiometry from the balanced reaction, as well as what we refer to as an ice table, and a little bit of algebra to figure out the other concentrations or whatever it is we need to solve for in the problem. Now, I'm not going to click on this link, but ice tables always makes me think of Vanilla Ice's Ice Ice Baby song that came out back when I was in college. And so if you want to listen to it while you do the notes, have fun with that. Oh, there's Boz. Hi, Boz. You want to say hi to everybody? He is helping me today. Hopefully he'll move his nose. Can he move B? Thank you. Okay, so what we mean by an ice table is, oops, nope, oh, I didn't mean to click on that, crap. Well, I guess we're gonna, no, okay, can't download that. All right, here we go. There we go. What we mean by an ice table is, ice stands for initial, change, and equilibrium. So we can be talking about either pressures or concentrations, just depends on whether we're dealing with gases or aqueous solutions, but initial concentration or pressure of all of the substances, then how they change as the reaction proceeds towards equilibrium, and then finally what their concentrations or pressures are at equilibrium. So just depending on what information we're given and what we're trying to solve for, we can use initial concentrations and their changes to determine equilibrium concentrations, or we can use equilibrium concentrations to ultimately find the Kc, or again we can use equilibrium pressures to find Kp, because again whether we call it pressure or concentration, we solve them the same way. So we're going to do 3 different types of problems, each with different things going on, so you can kind of see how we use this. And on the short answer section of the AP exam, they always want to see you set up an ice table. You will not get full credit if you just do the algebra without showing the ice table. So make sure you set it up, and we'll be using this all throughout chapter 17 as well as our acid chapter in our next unit. So we use ice tables quite a bit. All right, so here's our first reaction or problem. We have sulfur trioxide decomposing, and we're not changing the pressure, so we're not really worried. We're not changing the temperature, so we're not really worried about that. But it's telling us that the sulfur trioxide has a partial pressure of 0.5 atmospheres, and then at equilibrium, it only has a partial pressure of 0.2 atmospheres. And we're going to use this information to determine not only the Kp, but in order to find the Kp, we have to come up first with the equilibrium pressures of the other substances. So here's our balanced reaction, because again, this does involve a little bit of stoichiometry from our coefficients that we get balancing. So the I, again, stands for initial. So all we know is that the initial pressure of our sulfur trioxide is 0.5 atmospheres. And unless it tells you otherwise, we can assume that the initial pressures of our products before the reaction has started is obviously going to be 0. We haven't made any products, so there's no pressure. Then as the reaction starts to occur and the sulfur trioxide starts to decompose, its pressure is going to go down as the sulfur dioxide and oxygen's pressure are going to increase, like those graphs we were drawing in the notes the other day. So our change in pressure is the sulfur trioxide is going down by 0.300. And the way I know that is because up here in the problem it tells us that the equilibrium pressure of the sulfur trioxide is 0.2, and I'll pull that up here in just a minute. So if the sulfur trioxide pressure is decreasing by 0.3 because it's decomposing and forming sulfur trioxide in the same ratio, so for every 2 moles of the SO3, we are forming 2 moles of SO2. That means that the sulfur dioxide is increasing its pressure by 0.300, but the oxygen, because there's a 1 here, its pressure is only going to increase half as much as the sulfur dioxide. So its change in pressure is increasing by 0.150. And again, we can fill that change out because of what it said up in the problem, that the equilibrium pressure of the sulfur trioxide, once it comes to equilibrium, is 0.2. So that's how we came up with the fact that the SO3's pressure decreased by 0.3 atmospheres. And so then if the SO2 increased by 0.3 and it was originally 0, that means at equilibrium its pressure is going to be 0.3, and then the oxygen's is going to be 0.15. So now that we've determined what the equilibrium pressures are of all of our substances, we can finally plug some numbers into those equilibrium expressions we've been writing, which the equilibrium expression, since we're dealing with pressures, we have Kp, and again we do the products raised to their coefficients over the reactants. So we have the pressure of the SO2, and because there's a 2 here for a coefficient, that's squared, times the pressure of the oxygen over the pressure of the SO3, and again because of that 2 for the coefficient, we square that. So we plug in our equilibrium. We plug in our equilibrium pressures that we just determined from our ice table. So for, oh, there's Boz's nose again. Bozzy, you're in the way, buddy. Oh, little burp there. Boz, Watch out, B. Come on, thank you. So at equilibrium, we plug in SO2's pressure of 0.3, and we're going to square that. And then the oxygen's pressure of 0.15. And then in the denominator, the pressure of the SO3, which is 0.2, and we square that. So we just do a little math, doing our taking the squares of those, and we come up with an equilibrium constant of 0.3375. Okay, so that's how we come up with those equilibrium values. And just a little practice from the other day, since that value is much smaller than 1, we would say that this reaction is going to favor the left side, or our reactants. It's not going to form a whole lot of products. It's going to stay mostly on the reactant side. Okay, so again, we use this ICE table to figure out the equilibrium pressures and then plug those into our equilibrium expression. So that one's a pretty straight up reaction. The second reaction gets a little more complicated. Here we have bromine and chlorine forming 2 BrCls, and it gives us the equilibrium constant this time of 7.0. So it tells us, besides the equilibrium constant, it says that the initial concentration of the reactants are each 0.15 atmospheres, and what we're going to try and figure out is the equilibrium concentrations of all of these substances. So I'm going to, let's try this again. So here's our reaction again. And setting up our ICE table, we know our initial concentrations for both the bromine and the chlorine are 0.15. And again, unless it tells us otherwise, we're going to assume that initially we have no product, that it's starting at 0. Now for this one, we don't know how much the pressures are changing because it doesn't give us an equilibrium pressure. I know it says concentration up there, but technically it's pressure. We don't know the equilibrium pressure, so we don't know what their change is. So we're going to let the change of the pressures equal X. Okay, so for the bromine and the chlorine, since they're both one-to-one relationships, they're both going to go down, because again, as the reaction proceeds, the reactants are going to decrease, products are going to increase. So both the bromine and the chlorine's concentrations are going to decrease by a factor of X. So we have a minus X for the bromine, a minus X for the chlorine, but because of this 2 here in front of the BrCl, its pressure is going to increase by a factor of 2x. So again, we're forming products, so the pressure or concentration of the products is increasing while the pressure or concentration of the reactants is decreasing. And we have this 2x here because of the coefficient 2. So then at equilibrium, for both the bromine and the chlorine, their equilibrium concentrations or pressures are going to be 0.15 minus x, and then the BrCl pressure is going to be 2x. And those are the values we're going to plug in to our equilibrium expression. So again, we set up our equilibrium expression with our product raised to its coefficient. So we have the pressure of the BrCl squared over our pressures of our reactants raised to their coefficients. So we have the pressure of Br2 times the pressure of Cl2, and they're both raised to the first power. So then plugging in our values that we have up here in our equilibrium section, for the BrCl, we have 2x squared. And then we have, since both of these are exactly the same, instead of writing them separately, we can just say 0.15 minus x squared. Okay, now we can only do that because they're both exactly the same. So that makes our math a lot easier. If these were not the same, if these values were different, like say the CL, if it were different, yeah, this is why I typed this out. I started this by writing these notes, and it ended up all like that. So if one of these values here for one of the reactants were different, then we'd have to use the quadratic equation to solve. And I know you all know how to do that, but we're not going to do that. So, we would have to use the quadratic equation. But luckily, these are both the same. So what we can do then is we can take the square root of both sides to get rid of the square. So that gives us then 2x over 0.15 minus x, and the square root of 7 is 2.65. So that makes our math a lot easier. And then when we solve for x, so we'd multiply both sides by 0.15 minus x and distribute, and then solving for x, again, that's all algebra I know you guys know how to do. That ends up giving us x is equal to 0.0855. So now that we know what x is, we can plug that back in up here with our equilibrium concentrations. And so for the pressure of the bromine and chlorine at equilibrium, we take 0.15 minus the 0.0855, and that gives us an equilibrium pressure for our reactants of 0.0645. Up, and here comes Ozzy. There's Ozzy. Okay. Hi, baby. So we sorry. He likes being petted, so he's trying to make me pet him. Okay, so subtracting out x, the 0.0855, that gives us equilibrium pressures for the bromine and chlorine of 0.0645, and then plugging in the 0.0855 up here for the BRCL and multiplying it by 2, that gives us an equilibrium pressure of 0.171. So those are our equilibrium pressures. And again, because both reactants had the exact same values for their equilibrium pressures, we could just take the square root of both sides, and that saves us from having to do the quadratic equation, which AP is getting away from making you use the quadratic equation, but just be aware you may need to use it if you can't take the square root of both sides. Now, like I said, AP is trying to get away from making you use the quadratic equation, and this is more the type of problem that they would use instead of making you use the quadratic equation. And when we have equilibrium concentrations that are very small relative to, when we have equilibrium constants that are very small relative to their concentrations, we can assume that the change in concentration is negligible, and therefore we, as I'll show you, we don't have to end up using the quadratic equation. So again, here we have nitrogen reacting with oxygen, forming nitrogen monoxide, and as you can see, this is a super small Kc, 4.8 times 10 to the negative 31st. And it gives us our initial concentrations of nitrogen of 0.33 molar and oxygen of 0.0081 molar. And just like the last problem, we're going to use the Kc to figure out their equilibrium concentrations, but because the Kc is so small, we'll get to make this a lot easier so we don't have to use the quadratic equation. So again, here's our balanced reaction. We have N2 plus O2 forming two NOs. So our initial concentrations, 0.33 for the nitrogen, 0.00810 for the oxygen, and our product, we have no product initially. Now again, we don't know what the change is. So just like we did in the last problem, we're going to let the change in concentration equal X. So again, our reactants, since they're both 1 to 1, they're both going to decrease by a factor of minus X. But because our NO has a 2 here, it's going to increase by a factor of 2X. So again, we have to pay attention to our coefficients. So that tells us that at equilibrium, we have 0.33 minus X for nitrogen, 0.00810 minus X for oxygen, and 2X for nitrogen monoxide. So we're going to take those equilibrium values and plug them into our equilibrium expression. So this time we're dealing with concentrations instead of pressure. So we have Kc is equal to NO2 squared over N2 times O2, and then we plug in our equilibrium values that we got right here. So again, we have 2x squared over 0.33 minus x times 0.00810 minus x, and that is equal to 4.8 times 10 to the negative 31. Now, unlike the last problem, if you notice, where'd my pen go? These two values, the 0.33 in our denominator and the 0.00810, they're not the same. So we can't say that they're squared, and we can't just take the square root like we did in the previous problem. Now, if this equilibrium constant was not so small, we would have to deal with the quadratic equation and set this equal to 0 and solve for x that way. But because this is so small, we can say that this change in concentration is negligible. So we can just get rid of that. Let me try and clean that up a little bit. Let's try that again. This is why I'm not using the pen. So we can say that this is negligible. So instead of having to set up a quadratic equation and factor and all that stuff, we can just forget about the change in x and go with 2x squared over 0.33 over 0.00810 is equal to 4.8 times 10 to the negative 31st. And that makes the math a lot easier. Now, the one thing, and I've done this a lot myself, is when we have 2x in parentheses squared, that equals 4x squared, not 2x squared, but 4x squared. And then we have, again, we got rid of the minus x to make the math a lot easier. So we have 4x squared over 0.33 over 0.00810. And then we just solve for x. After multiplying these and dividing by 4 and then taking the square root and all that algebra stuff, we end up with x is equal to 1.79 times 10 to the negative 17. So now that we figured out what x is, we can bring that back up to our equilibrium values and plug that in. And as you can see, look at how tiny x is. X is times 10 to the negative 17. So even if we wanted to, if we took 0.33 and subtracted this value, it's not going to change anything. It's still going to be 0.33. So that's why we were able to say this equilibrium is so small that the concentration of the reactants really aren't going to change at all. That's what we were talking about the other day. When we have a small equilibrium constant, it favors the reactants. So at equilibrium, we can say that the nitrogen's concentration is still 0.33. oxygen's concentration is still 0.0081, because again, even if we subtracted this X from it, it's not going to change this value. And then to figure out the nitrogen monoxide's concentration, we multiply the 1.79 times 10 to the negative 17th by 2, because we have 2x here, and that gives us a concentration of 3.58 times 10 to the negative 17th. So again, usually when you can't take the square root of both sides like we did on the second problem, it will usually be a reaction where the equilibrium constant is so small we can make that change in X negligible for the reactants, because again it's going to favor the reactant side and keep mostly the reactants, and that will make our math a lot easier. But just know there could be a chance where you can't do that and you have to use the quadratic equation. All right, so again, try and do the homework that goes along with this, and